In this video, I want to take a look at a couple of very special triangles and their trigonometric ratios. The two triangles that we're going to consider are an equilateral triangle and a triangle that we can cut out of a perfect square. So I'm going to take the square and get rid of half of it, leaving me with the triangle that I'm interested in. Now, the square, I want to have sides 1. This side right here is the hypotenuse. That side square is going to be equal to 1 squared plus 1 squared. So that side squared is going to be equal to 1 plus 1, which is 2. And taking the square root of both sides, I get that that side is equal to the square root of 2. So let's go ahead and change that. A square that has sides of 1 has a diagonal of the square root of 2. If you then delete half the square, you're left with a triangle whose hypotenuse is the square root of 2. All right, let's take a look at the other triangle. With this one, if I let my sides be 1, then half the bottom would be a half. Now I can do this with these values, but it's actually easier to use the value of 2. I'm going to go ahead and do it with the values of the sides of 1. Notice that because this is an equilateral triangle, the bottom is also 1, and I'm looking at half of that bottom. If I erase half of this triangle, I'm left with this. And my third side is going to be found by saying that 1 squared, the hypotenuse squared, is equal to 1/2 squared plus my unknown side squared. 1 squared is 1, 1/2 squared is 1/4, and that gives me, oh, that should be a plus. That gives me an equation that I can solve, so that subtract 1/4 from both sides. I get my third side squared is equal to 1 minus a fourth, which is 3/4. And if I take the square root of both sides, I get that my unknown side is equal to the square root of 3 over the square root of 2, or the square root of 3 over the square root of 4, which is the square root of 3 over 2. So this third side here is the square root of 3 over 2. And we can get rid of our scratch work. Now the other thing to notice about an equilateral triangle is that all three angles are also the same. So since triangles have angles that add up to 180 degrees, we have A plus B plus C is 180 degrees, but A plus B plus C, A, B, and C are all the same. So B is the same size as A, and C is the same size as A. So I get 3A equals 180 degrees, or A equals 60 degrees. That means that this angle right here is 60 degrees. Because what's left once I cut my like my triangle in half, and I only look at the left-hand side of it, I have a 60-degree angle here and a 90-degree angle here. That means this angle up here must be 30 degrees, because again, a triangle's angles must add up to 180 degrees. So I'll erase my scratch work again. The other way I could have come up with this 30-degree angle is by noticing that the original triangle has this top angle has been cut in half, right? I've bisected the bottom, but it's exactly the same length on all three sides, so bisecting the bottom also means bisecting the angle. So this originally was a 60-degree angle, and I cut it in half, so it's a 30-degree angle. Now in my square, or what's left of my square, I had a square, and that means all four of my angles are 90. But I cut these two in half. So both this angle and this angle are 45 degrees. So with that information, we can now find the sines, cosines, tangents, cotangents, secants, and cosecants of 30, 60, and 45-degree angles. So let's get started. Because I'm using this diagram here, I can just pick off my 30-degree angle and look at its opposite over hypotenuse. Actually, I said I was going to do this with different lengths, didn't I? Let's go ahead and do it with the diagram that I've got here first, and then I'll show you that it doesn't matter what length you use, you end up with the same result. The sine of 30 degrees, I also want to put this over here, 30 degrees, 45 degrees, and 60 degrees. We're actually going to fill this in later with 0 degrees and 90 degrees, but we're not going to talk about those just now because those are sort of another special case. We kind of need a unit circle approach to talk about those because of the way the sine is defined. Sine is opposite over hypotenuse. And if your opposite over hypotenuse is based on if the result is 0, then what did the opposite have to be? 0, and there's no triangle involved, right? So we'll come back to those in a little while. So we're going to be looking then at the sine, cosine, tangent, secant, cotangent, secant, and cosecant of these three angles. For my 30-degree angle, my sine is opposite over hypotenuse, which is a half. Also for my 30-degree angle, my cosine is adjacent, that's this one, adjacent over hypotenuse. So I get the square root of 3, nope, down here, the square root of 3 over 2. I've moved my cosine and my tangent down just a little bit. You'd think that by now I'd have figured out that I need more space, but I haven't, so I just adjust as I need, as I go along. All right, tangent for this 30-degree angle, opposite over adjacent, is 1/2 over the square root of 3 over 2. I'm going to do some scratch work on this one first. Opposite over adjacent is 1/2 over the square root of 3 over 2, which simplifies to 1/2 times 2 over the square root of 3, which is 1 over the square root of 3. So the opposite over adjacent, the tangent of 30 degrees, is 1 over the square root of 3. Now, again, if you choose to, you can write this as root 3 over 3, and you may see it that way sometimes, but I don't care. If you want to leave that as 1 over the root of 3, that's absolutely fine. That's what I would do. All right, now using the same triangle, I'm going to take the sine, cosine, and tangent, find the sine, cosine, and tangent of the 60-degree angle. Well, opposite of 60 degrees is the square root of 3 over 2. Hypotenuse is 1. So the sine of 60 degrees is the square root of 3 over 2 over 1. The cosine is adjacent over hypotenuse. That's 1/2 over 1. So that's a half. And the tangent is opposite over adjacent, or root 3 over 2 divided by a half. This time I'm going to get root 3 over 2 times 1 over 2. That's the square root of 3 over 1, or just the square root of 3. All right, now I'm going to go back and relabel this triangle using sides of length 2. And the reason for that is that I want the sides that I have, let's see, I'll put a 2 here and a 2 here. And if I cut that in half, then this piece has a length of 1, and that gives me an integer to work with. As it turns out, it doesn't matter, but this is more conventionally how this is done. So if I make that a solid line now, I never did do that on the other diagram, and I'll include my square to show that this is a right triangle. Then I can find the third side here as being, let's see, I have 2 squared equals 1 squared plus something squared, or 4 minus 1 equals something squared, that's 3, so the square root of 3 is my missing side. Okay, Now when I find my sine, cosine, and tangent, let's put 60 degrees down here and 30 degrees up here. When I find the sine, cosine, and tangent of 30 degrees, the sine is 1 opposite over 2, the hypotenuse. That's the same thing as I got. Here I had 1/2 over 1. Here I'm getting 1 over 2. Because these are similar triangles, the sides of this triangle are twice the lengths of the sides of this triangle, and so their ratios are going to be the same. Let's just double check that. What's the cosine of 30 degrees? Well, that's adjacent over hypotenuse, square root of 3 over 2. And that's the same thing as I got here. Now my drawings don't really indicate this scaling, do they? But it doesn't matter, because once again, these are just a tool. I can just imagine that this is actually twice the size it really is. In fact, it's conventional, actually, to use a side length of 2 rather than a side length of 1 on the equilateral triangle. So I'm going to redraw this triangle. Oops, that's the 60-degree angle, and the 30. Sometimes when you don't have enough space, you can put an arrow that indicates that the angle I'm pointing at is the 30-degree angle. And then I'll replace these ones with this one. If I can get my pen to work, there we go. So this is my 30, 60, 90 triangle. There's the 90. And here's my 45, 45, 90 triangle. I found the sine, cosine, and tangent of 30 degrees and 60 degrees. I'm just going to do one more to verify that this triangle works just as well as the previous one. Let's find the tangent of 60 degrees. Here's my 60-degree angle. Tangent is opposite over adjacent, so I'll have the square root of 3 over 1, or the square root of 3. So I get all the same measurements using this version of the triangle as I did using the other one. Okay, that's 30 and 60. Let's fill in this column now. To do that, I'm going to erase my rationalized version of 1 over root 3. That square root of 3 over 3, I'm just going to erase that. That gives me the room I need to put the ratios for 45 degrees in. Well, now in this case, I'm going to have the sine of 45 is 1 opposite over root 2. And for this angle, because it's the same measurement, the opposite is going to be 1, also over root 2 for sine. So opposite over hypotenuse and opposite over hypotenuse is the same. So I have 1 over the square root of 2. The cosine is, let's go ahead and go with this 45-degree angle. Opposite was 1 over the hypotenuse, root 2. Adjacent is also 1 over root 2. So in this case, I have 1 over root 2 for both the sine and the cosine. Opposite over adjacent, though, is 1 over 1. And that's just 1. We'll go back and fill in the columns for 0 and 90 degrees in a little while. Not in this lecture, not in this video. It's going to be a while before we get to that. But we will come back and fill these in. Right now, I want to point out that these values are what we consider the important exact values of the sine, cosine, and tangent for these three angles. And as you go through the rest of this course, you'll be expected to be able to come up with, for example, the cosine of 45 pretty quickly. You could absolutely use a chart. The more you use these values, the more you'll just sort of find them coming to mind. You'll be committing to them to memory without really even trying. There's a nice thing to recognize here. There are actually several things. One is that I can continue my chart. I'm going to do it not the way I really like it this time, but it's sort of, in order to get all of these values in here, I kind of need to do it this way. But then I'm also going to go back in and write my chart in this form, just for reference. I won't need this going forward necessarily. Okay, now I've just written the ratios down here. I haven't actually written what they are. The reason I've done that is because I want to be able to fill in this value here without necessarily computing it. Sure, I could say, well, for 30 degrees, cotangent of 30 is adjacent over opposite. That's going to be root 3 over 1. or just root 3. But also, remember that I could say that since tangent and cotangent are reciprocals of each other, the value of tangent and the value of cotangent are going to be reciprocals of each other, that these two functions here, these two ratios, are these two ratios here, and I could just take all of the values I find in this column and flip them over. I don't need to actually go compute them. 1 over 1 is 1, and 1 over the square root of 3. Equally, cosine and secant have that relationship. So whatever I see in the cosine row, I can flip it over to get what I need in the secant row. Square root of 3 over 2 becomes 2 over the square root of 3. 1 over the square root of 2 becomes the square root of 2 over 1, or just the square root of 2. And 1 over 2 becomes just 2. Lastly, since sine and cosecant are reciprocals, these three values, when I flip them over, can go in this row. And I get 2 over 1, root 2 over 1, and 2 over root 3. So the first point that I want to make here is that I don't really need these in my chart. If I was going to put this on a note card, I would leave these bottom 3 rows off because I can figure them out really easily from these top 3 rows. Now, here's another special relationship that we haven't talked about yet. That is this one here. Tangent of theta in every single case, and you kind of have to squint to see this one. It's not quite so obvious. But the tangent of theta, 1 over the square root, this tangent of 30 is 1 over the square root of 3. And if you take the sine and divide it by the cosine, the denominators cancel, because the reason that happens is if you flip this and multiply, this becomes the numerator, it cancels with the denominator. That becomes 1 over the square root of 3. And look at what tangent is. Okay, let's do it for this one. If I take the sine and divide it by the cosine, well, these have the same value. Anything divided by itself is 1. If I take the sine and divide it by the cosine, the denominators cancel. They're the same. So I get root 3 over 1, or root 3. So this is another very interesting relationship. It says that the tangent of an angle is the same as what you would get if you take the sine of an angle and the cosine of an angle and divide them. Specifically, the tangent of an angle is the sine of an angle divided by the cosine of an angle. Isn't that interesting? It turns out that because they're reciprocals, the cotangent of theta is cosine of theta divided by sine of theta. That shouldn't come as a surprise because, first of all, cotangent is the reciprocal of tangent. So cotangent is equal to 1 over 1 over tangent, and cosine over sine is equal to 1 over sine over cosine. So not terribly surprising. That said, down here in the corner, if I write cosine of theta is equal to sine theta divided by cosine theta, we have another identity. This is something that you're going to see quite a bit more going forward in this class. Right now, it's just an interesting observation. But here's something else I can say. I don't need this row in this chart. I only need the top 2. To find the third row, I just take this value divided by this value. That gives me this value. In every case, this value divided by this value gives me this value. Once I have these 2 rows, I can find the third row, and then I can find the bottom 3 rows by flipping over the top 3 rows. So I really only need these 2 rows in my chart. The same will hold for the 0 and 90 when we get there. Okay, one last thing for this video. It's included in the title of this section, or this subsection, but I didn't include it in the title of the video right at first because it's really kind of a minor thing as far as I'm concerned. I'm much more interested in these exact values than I am in decimal approximations. When you're working with 30, 60, and 45-degree angles, I expect to see these exact values. That shouldn't be the square root of 1. What should it be? It should be cosecant is 1 over sine, so it should be the square root of 2 over 1, which is the square root of 2. My apologies. If you find errors in my videos, I do hope you'll let me know. Just send me a quick message. Sometimes I can fix them fairly quickly, and then I'll put a corrected version up. Anyway, what was I saying? I was saying that when you're working with 30, 60, and 45-degree angles, the sine, cosine, tangent, cotangent, secant, and cosecant of those angles can be found from this chart, and I will expect, for the most part, that you use those exact values. There are times, as in the next section or the next subsection, when we talk about applications, that we actually aren't going to care about exact values. But outside of those situations, I would expect to find exact values in your work, not decimals. However, we're not always going to be working with 30, 60, and 45-degree angles. For example, I might ask you to find the sine of 2 radians, or the sine of 37 degrees. And in that case, you really kind of need to use your calculator. In this case, you need to make sure it's in radian mode, and then you just type in sine 2. In this case, you need to make sure it's in degree mode, and then you just type in sine 37. Hit enter. It'll give you a decimal approximation. And your calculator has a sine, cosine, and tangent button, but it doesn't have a cotangent, secant, or cosecant button. So that's why this part is in this section. If I ask you, for example, to find the cosecant of 37 degrees, you're going to need to have the information available in your head that that's just like 1 over the sine of 37 degrees. And then you can put into your calculator 1 divided by sine 37 and hit enter. If I ask you to find the cosecant of 2 radians, well, that's 1 over the sine of 2 radians. So you type in 1 over sine of 2 and hit enter. But in both cases, you need to make sure that you're in the right mode. Here, because there's no degree sign, there's no degree symbol in the problem, I need to make sure that I'm in radian mode before I type this into my calculator. Here there is a degree symbol, so I need to make sure that my calculator is in degree mode before I type this in and hit enter. That's really all I'm going to say about calculators. I have no issue with you using a calculator to check your work, but when you write your answers for me, I want them in exact form whenever that's possible. There are times when I'm working with degrees or radians outside these values, 30, 60, and 45, that I just need to use a calculator because there's no simple way to get the values in this form. There is something else I forgot to do, and so I'm going to do that kind of right at the very end here. I've been doing all of this work in degrees. My chart here is just in degrees. But notice that I can convert any of these, and in fact, I'll convert all of them, from degrees into radians. 30 degrees. Remember that I want to cancel my degree symbol, so I'm going to put the degrees on the bottom. I have pi over 180. Get rid of my degrees. Reduce this. 30 degrees is pi over 6 radians. So pi over 6 is one of those really common angles. It's just that it's not in a form that we're familiar with, so it's not going to look familiar. It's not going to look common at first. I think I'll erase some of my calculator stuff here. And then I'll convert the other two. 45 degrees is when I multiply it by pi over 180. The degrees cancel. And then let's see, 5 goes into 45 9 times. 5 goes into 18 3 times with a remainder of 3. 5 goes into 36 times, and then 9 goes into 36 4 times, so I get pi over 4. 45 degrees is pi over 4 radians. Lastly, 60 degrees is not equal to, not yet, pi times pi over 180. Cancel the degrees. And this time I have 60 goes into 60 and 60 goes into 80. So 60 degrees is pi over 3. So now when I ask you for the tangent of pi over 4, you'll be able to look along this row and down this column and tell me that it's 1. When I ask you for the secant of pi over 3, you'll be able to look along this row and down this column and tell me that it's 2. I'm going to ask you to fill in a chart that looks just like this. You can just copy this out onto paper, or you can use the PDF that I've provided in the assignment, and then you've got a nice, neat little template to fill in. I want you to fill that in. Even though I've done it for you here, I want you to fill it in because I want you to have access to it as a resource. Fill that in. Right now, you can leave this column and this column empty. We'll come back and fill those in later, and I'll ask you to turn that in again. But for right now, fill this in, even if you just do it by copying down what you see here, and upload that as a turned in homework assignment. When you get it back, there may be some corrections. It depends on how you fill it in and whether you do it correctly or not. And then make those corrections and hang on to it. Hang on to that page. First of all, that means you don't have to recreate it when you fill in these 2 columns here. You don't have to recreate the middle 3 columns. You could just reuse the template, reuse the page that you've already turned in with corrections. Number 1. Number 2, it'll serve as a very nice reference. It's kind of like having a cheat sheet. You can write other notes all over that page, perhaps on the back. It depends on whether you're using analog paper or digital paper. But I am going to ask you to turn that in so that you have written those values out at least once, and you have that access to that as a resource. All right, in this video, we've talked about 2 very special triangles, the 30-60-90 triangle and the 45-45-90 triangle. From those 2 triangles, and I showed you how I derived or how I got those triangles from an equilateral triangle and from a square. From those 2 triangles, we found the sine and cosine of the 35, 40, and 60 degree angles. From the sine and cosine, we can find the tangent. And from sine, cosine, and tangent, we can find cotangent, secant, and cosecant. We also converted the 30, 45, and 60 degree angles into radians. And these are all very common now, both in degrees and in radian form. These are very common angles, so be familiar with those. The way I remember the 30, 45, and 60 is that the degrees has a 3 in it. The opposite one has a 3 in the radians. If the degrees has a 6 in it, the opposite one has a 6 in the radians. And the 45 has a 4 in both versions. Now that's a silly little mnemonic, but it works for me. 0 and 90 are a little different. We'll come back and fill those in later. For now, that's all I've got for you for this video.